Broadcast is now starting. All attendees are in listen-only mode.
Well, good afternoon, good morning, or good evening, depending on where you are in the world. My name is John Studley, and I'll be moderating this webinar this afternoon. Today's webinar is identifying polymorphism with in-situ Raman spectroscopy as a screening tool, and it's kindly sponsored by Technobis crystallization systems and Tornado spectral systems. So before we get started, a couple of administrative points. We are recording the session, and we'll share this with you tomorrow along with a PDF of the slides. Sometimes this goes into spam, so please keep an eye on your spam folder to make sure it's not ended up in your spam. And we'll also put a link to the webinar in our webinar archive on the Scientific Update website. If you have any questions, we've actually got two presenters today. If you have any questions, if you type them into the questions box on your webinar control panel, I will relay the questions to the speakers at the end of the session rather than interrupting them as we go along. And if you have any connection issues today, sometimes we have kind of dipping out. If you switch the audio off and on again, that usually fixes 99% of the issues. If you really do have some significant issues, I suggest you log out and re-log in again. Before I introduce our speakers, I'm just going to launch a quick poll. So Technobis and Tornado are interested to know whether you've worked with them or whether you're currently customers. So I'm going to launch the poll, and I'd appreciate it if you could quickly just answer those questions. Okay, I think we've got a reasonable number voted. Let me close the poll. So it's my pleasure to introduce our two speakers today. We've got Dr. Thomas Kendall from Technobis Crystallization Systems and Mark Kemper from Tornado Spectral Systems. So the first speaker today is Thomas. Thomas is an application specialist at Technobis Crystallization Systems. He's got a PhD in chemical and process engineering from the University of Strathclyde, and he's previously worked in a CRO investigating complex solid form and crystallization development. And he has around 10 years of experience in the pharmaceutical and crystallization area. So I invite Thomas to give his half of the presentation on identifying polymorphism with in-situ Raman spectroscopy at screening scale. So over to you, Thomas.
Thank you, John. Okay, so my talk today, or my part, is going to be on identifying polymorphism with the use of in-situ Raman at small scale. So I'll start with a brief introduction about Technobis, as well as then a small introduction on polymorphism, screening for polymorphs, as well as the importance of polymorphism within pharma. How you can detect polymorphs, as well as the benefits of using PAT at small scale, how that is used to capture complex crystallization behavior, as well as monitoring rapid polymorphic changes, and then ending on a piece about carbamazepine, which we can use both Raman and in-situ microscopy to detect polymorphic conversions. So Technobis Crystallization is a company that specializes in platforms for accelerating crystallization research. So this can be solid form screening, crystallization development, but as well as looking at how to prevent crystallization from happening. So particular of interest in, say, formulation or oil and gas. So this is done using a number of unique and proprietary technologies, and we have major footprints in pharma, agro, and fine chemicals, but as well food, personal care, and academia. And the two products that we used as part of some of the research done in this presentation were the Crystal 16 and the Crystalline. So both of these systems are multi-reactor systems, so you can program multiple temperature profiles in each. Both have a relatively small footprint with little training required to use. All the software can be automated as well, so you're able to program your experiment, go home at the end of the day, and come in the next day with data there ready to analyze. All the reactors are fairly standard, cheap, and disposable, so they're stuff you can get from Fisher or VWR. All our analytics are non-invasive, so they don't actually are not in the vial, but through the vial, and that allows us for no cleaning to be needed. And in terms of analytics, the Crystal 16 has transmissivity data, which is used for collection of solubility, and the Crystalline has in-situ camera to visually see what's happening in your experiment, and can be applied with Raman, which is the case of many of the experiments we've done here. So in pharma, many small molecules are put into the solid formulation, and this is because it offers a benefit for ease of administration through accurate, reproducible, and consistent dosing, and improved stability, ease of transport, and an improvement in patient compliance to actually take the drug. But when selecting a solid form to develop, they have to balance between two sets of factors: biological factors, so such things as solubility, bioavailability, and safety, determining how well it performs for the patient, as well as economic factors such as density, flowability, filterability, and overall how well it processes. And they have to try and address and optimize a solid form to hit as many of these properties as possible. And describing polymorphism can be done based on sort of the internal crystal structure. So in amorphous solids, what you have is a lack of long-range order, so the molecules are more just packed together rather loosely. For polymorphism, you can have different packings of the same API within the crystal lattice, giving remarkably different physical chemical properties. If you introduce a second component, which is a solvent or water, you form solvates or hydrates. This is where the liquid is incorporated into crystal structure and stabilizes the lattice. And then when a secondary molecule is incorporated but is not a liquid, it can form either a salt or co-crystal. And this is defined by whether there is an exchange of the bonding proton. If there is, we get ionic bonds forming, and this forms a salt. And if there is a shared proton between the two different molecules, that results in a co-crystal. But the landscape for a solid form can be very complex. So you can start with your initial molecule, and from that you could maybe find 3 solid forms as well as 2 solvates. You would also want to look at what other salts and co-crystals are out there for patent protection. So you may form salt A and B with different counterions. However, it's sometimes considered, and wrongly, that by forming a salt or a co-crystal, you actually reduce the chances of polymorphism. And this isn't the case. You'll tend to find that if you're getting polymorphs of the main molecule, you're also likely to get polymorphs of the salts. I mean, in some cases, salt solvates or co-crystals and co-crystal solvates being formed. So when you're wanting to investigate what polymorphism is out there, you obviously look as many different techniques as you can. And this is a very famous sort of diagram that I've taken from the reference here, which shows sort of the general trend of experiments that you conduct, as well as the time and whether they form more kinetic metastable forms or push towards more thermodynamic forms. And the adage of Walter Macron seems to hold quite true in my experience of the more time and money you spend looking for solid forms, the more you are probably going to find. And it was a running joke that usually the last XRPD you ran was going to be a new form. Is just that sort of instance. But you don't have months to spend looking for solid forms. So you do have to be sort of conservative with sort of how many you want to try and hit and looking at as many conditions as possible. And being able to introduce analytical technologies in situ for a lot of these solvent experiments can be very beneficial. And the case for maybe not looking hard enough is the famous case of ritonavir. And this is famous because it's one of the only cases of polymorphism making it out into the public. So ritonavir is a HIV drug discovered in 1992, so just after the HIV epidemic in the US, and was approved for FDA in 1996. Originally produced as Norvir, it's formulated as a gel capsule and as a liquid. But in 1998, many products started to fail their dissolution tests. They had done polymorphism screens and decided that form 1 was what they wanted to take forward. And what they began to find is the capsule began precipitating during storage. And what this was an undiscovered form 2 with less soluble, which was less soluble than the solvents used for the formulation, and resulted in crystallization and then a lower effectiveness in the patient. From then on, only form 2 could be found in the facilities that were previously performing form 1. So seeds of the form 2 had made it out into the plants and had to be reworked as a suspension formulation. And this cost out about $250 million. And there's a very interesting podcast by Chemistry World on this that I recommend. Another consideration with polymorphism is from a legality standpoint. So this is a case of a former Sanofi drug candidate where they had conducted a polymorphism screen and identified 3 polymorphs. A generics company using the Crystal 16 conducted a polymorphism screen using shock cooling, so fast, slow cooling, slow evaporation, and thermocycling with a range of different functionality solvents, including chlorides, acetates, nitriles, and alcohols. And from this, they were able to identify an additional 5 polymorphs, undermining the patent of Sanofi and being able to go direct to market. So detecting polymorphism is of high interest. And this can be done using 3 sort of specific ways, of one being spectroscopic, the second being thermo, and then a final being an X-ray scattering. So using UV vis, FTIR, and Raman, you're able to detect differences within the spectra. So the sample is bombarded by light, it absorbs energy based on the specific vibrational, rotational, or stretching frequency of a bond. And in one configuration, this bond might have a certain degree of freedom in order to do those motions, and the energy will be set. However, by moving into a different crystal configuration, this now loses a certain degree of freedom due to maybe the molecule being positioned differently, and now it absorbs a different amount of energy, changing the wave number of the energy absorbed. DSC is based on thermo properties, so this can be that different polymorphs have vastly different melting points. It is possible to see melts and recrystallizations using DSC. And then finally, XRPD and single crystal X-ray diffraction, which is measuring the diffraction pattern of X-ray scattering within the crystal lattice. And whilst XRPD and single crystal are the most definitive ways of detecting polymorphs, Raman can be used to track in situ solid forms, so being able to detect what's going on. And the benefits of starting earlier can be quite big. So being able to do more, getting more information at an earlier stage with less material. So every experiment you do when you don't have a lot of material becomes quite valuable. It allows you to see potential problems on the horizon. So as you go through your drug discovery pipeline, you need increasingly larger manufacturing campaigns. And it's better to maybe identify that at a certain scale, problems might start kicking in of oiling out, gumming, and this can help you sort of reassess those before they become a bigger problem down the line. Choosing the right form, so it allows you to see if maybe another form which you previously hadn't seen is also present, maybe transcendental, maybe it's only stable for a few minutes, and this could be potentially a problem going up to scale. But it also adds a level of confidence. So if you've got a very good process that isn't giving you any problems, then having additional information confirming that this isn't a problem can be very valuable and helps you lock in a process early and overall shorten your time to get the molecule to market. And another big benefit of being able to introduce PAT at a low scale is the reduced amount of material you can save. So PAT has been shown to be a critical tool in crystallization development. It's used in practically every example of crystallization development for producing invaluable real-time information. However, these are typically introduced as bulky probes, and the smallest vessel that these typically are used with is 100 milliliters. So I did some calculations based on some experience I had, knowing that typically processes are between 5 to 20 volumes, and a volume is defined as 1 gram and 20 milliliters. So for a 20 volume process, 5 grams per experiment at 100 milliliters, or for 5 volumes, 20 grams per experiment. But by being able to work at 2.5 milliliter scale with the crystalline, you were able to reduce that significantly down to 125 mg for 20 volumes, or 500 mg for 5 volumes. And for one or two experiments, 5 grams might not be that much, but if you, depending on how complex the crystallization is, this can start to add up. So typically crystallizations fall into 3 categories. First being ideal crystallizations. This can be where there's no other polymorphs lurking around. It's quite easy. You can cool down and get a good yield. So this could be 2 small experiments followed by a few fine tuning. That can be between 30 to 120 grams for just an ideal crystallization. If you start having more problems, so a reality crystallization project where it has secondary forms, you need to do anti-solvent, so screening for that, addition rates. This can then start to ramp up even more to 60 to 240 grams. And what became known as with many people as an interesting crystallization project is something that gums, oils, has multiple polymorphs, forms needles that stick together and block filters and stirrings. And this can take a lot of material, so anywhere between 160 grams to 640 grams of material at the 100 milliliter scale. However, by being able to operate at 2.5 milliliters, you can reduce this down from 4 grams to 16 grams to conduct all these experiments which you would need to understand maybe a complex crystallization process. And some of these factors you can't see with Raman, so such things as oiling out or agglomeration need to be seen by camera imaging. And that's a similar problem of being only really usable at 100 milliliter scale. But with the crystalline, we can get down to 2.5 milliliters. And we can see the crystals. We can start to do some preliminary particle size analysis by calibrating the number of frames the number of pixels the crystal takes. We're also starting to see aggregation where crystals start to stick together. Will this need to be addressed further down the line? And these are information at 2.5 milliliter scale can be very useful for future design, as well as seeing big problems such as oiling out. And you can see really complex crystallization behavior at this small scale. So this is a case of where a molecule was doing a cooling crystallization, initially forming very small crystals, and these crystals over time started to become droplets. These oil droplets began to coalesce and grow in size, creating very high localized supersaturation, and crystals began to form inside these oil droplets. The oil droplets then crystals began to grow inside these, consuming the oil, and eventually the oil droplets aggregate even further, and we're left with just these giant rocks of aggregated crystals, which are really difficult to handle. So being able to detect form changes as well is very important. So in this case, we have mefenamic acid, which is a non-steroidal anti-inflammatory used in treatment of mild pain. It has 3 polymorphs, with form 1 being the most stable. Form 2 is really difficult to obtain and really difficult. It was really difficult to maybe even prove it exists because it converts so rapidly over time. So we were provided some mefenamic acid form 2, and were suspended in ethanol and stirred at 25 degrees C on the crystalline instrument, which was then hooked up to the tornado Raman. And we measured over 10 minutes the gradual decrease of the stretch at 1676 wave number over time until eventually it's no longer present, and we've fully converted to form 1 over the space of 10 minutes. And then finally, a case of carbamazepine, which has both optical and Raman spectral changes. So carbamazepine is used in a lot of research and is an anticonvulsant medication used in treatment of epilepsy. Has several forms, but 2 which have very different morphologies is form 2, which is a metastable in needles, which are in pharma needles are quite difficult to handle and unwanted. And form 3 is the thermodynamic form and has these sort of block-like crystals. So you can observe the physical change in morphology, but you can also observe the Raman spectral change going from form 3 to form 2 by several peaks. So we decided to use the crystal 16 to generate a solubility curve, identify and calculate the solubility, the supersaturation and concentration needed to generate, say, 4.0 supersaturation, and then conducted a cooling experiment, a rapid cooling experiment, by dissolving form 3 and then crash cooling to generate supersaturation as fast as possible. And with this, we were able to nucleate form 2 with these needles. Over time, this gradually starts to convert to give us these blocks, which are quite faint. And then gradually the needles start to disappear more and more, and we get just more and more blocks. And in the end, we just have large individual crystals of the form 3 converted. We can also see this change by the Raman. So we initially start with the form 2 peak, and then this gradually decreases over time, and we see an emergence of the form 3 peaks here and here. So we'll be able to track when something is fully converted and when we've removed all of the form 2, so we're confident in the crystallization process. So in conclusion, the control of polymorphism can have significant legal, economic, and biological impacts of a molecule. A PAT is a crucial tool for designing crystallization process that ensures polymorphic control, but can require a large amount of material at early stages of development when that material just doesn't exist. Implementation of these tools at early stages with little material, as low as 2.5 milliliters, can fast track molecules looking into the future and identifying problems before they become an issue. Using in-situ microscopy, it's possible to track complex crystallization behavior, including oiling out and polymorphic changes, as well as being able to, using Raman, rapidly in real time conversions of the solid form being tracked through changes in the Raman spectra. And now I'll hand over to Mark to discuss more about Raman.
Thank you, Thomas. So if you have any questions for Thomas, please type them into the questions panel, and I will relay them to Thomas at the end of the session. So let me invite Mark to present. There we go. While Mark gets his slides ready, let me just introduce Mark. He is the Director of Applications Development and Customer Success at Tornado Spectral Systems, Mark directs the customer success group, which is composed of 4 dedicated individuals who are committed to serving customers to make them successful with their Raman deployments. Mark's a chemist by training. He's been in industry for over 35 years, more than 25 of which have been spent in the instrument business, concentrating on molecular spectroscopy. In addition to process Raman, Mark's been involved in technologies such as handheld Raman, Raman imaging, NIR spectroscopy, FTIR, terahertz spectroscopy, and benchtop NMR. He's participated in 25 peer-reviewed and trade publications, and co-authored a book chapter dealing with spectroscopic applications. So over to Mark for the second part of this webinar today.
Okay, thank you very much for that introduction. I appreciate it, and thank you for listening in on my part of the presentation, which will be focused more on the Raman side of this application area. Just a word about Tornado Spectral Systems. We're headquartered with manufacturing and R&D in Canada. We do have a global presence. We have US field offices and 25 distribution partners globally that cover 45 countries. The technology that we use for this, the work that I'll present here, was something that was released commercially in Q2 of 2016 for industrial clients, and we've made consistent developments since then that have enhanced deployment. And our focus markets are in the pharmaceutical, biopharmaceutical, fine chemical, petrochemical, polymer, food, and other miscellaneous things like mining, where we find our applications. The Tornado solution is built on a bit of a different design, and if you want to discuss this more, you can get in contact with us. We'd be happy to go through this with you in detail, but I will just simply say at this point that we do a little bit different way of designing the Raman experiment that enables us to get 10 times better throughput with higher resolution. So the benefit to that is that customers are able to get faster measurements of the same quality. You can get 10 times better measurements or faster measurements by comparison for better process understanding and responsivity, more throughput for measurements. If you measure for the same amount of time, the signal to noise becomes better. That enables lower detection limits compared to standard designs. And it permits accomplishing measurements even with the reduction of laser power, such as in ATEX situations, which becomes vitally important working in explosive atmospheres in production areas. And we have equipment, all of our equipment is designed to be in situ process-related, for process-related analyses. So it basically involves putting a probe in place to detect in situ what's happening, making that measurement with the spectrometer, translating that into a signal, delivering that to a production control system, and in cases where the customers wish to do so, allowing for feedback that adjusts reactants or feeds or things like temperature, whatever the case may be, for the process adjustments according to the data that are being collected. There's 2 types of instruments. The one we use for this set of experiments is what you see there on the left, which is the HyperFlux Pro Plus. And we also have that same spectral engine in a more of a process footprint that you see there on the right. But they're both designed to be high throughput, 10 times better throughput than traditional designs, while maintaining resolution, which is vitally important for applications like crystallization. The resolution is extremely important. So both throughput and resolution become valuable. And the probe designs that we use for these types of experiments can either be non-contact or direct contact immersion probes. And that gives the flexibility for different sorts of experiments that need to be run. Using the same probe head, we can have a non-contact measurement, such as what you see at the top right, or we can put the probe directly into a vessel with the configuration that you see at the bottom right. Or we can adapt it to measurements such as what we did in this case with the Technobis device. So it's adapted to measurements that can be made specifically in these types of devices, like the crystalline, to have a PAT tool available for these types of experiments. So why is Raman a good tool for something like polymorph analysis or crystallization? Well, basically, Raman is an example of vibrational spectroscopy. Essentially, Raman responds to the vibrational energies of the chemical bonds that are present in the samples or in the molecules in the sample that you're measuring. So those vibrational energies are characteristic of the molecules that are present, but are also characteristic of the environments in which those molecules reside. And that becomes a very important point as we consider the issue of polymorph analysis and crystallization. There are different modes of motion that the molecules have. And you can see the principal ones here in this particular slide. There's stretching, either antisymmetric or symmetric stretching. There's scissoring, wagging, twisting, rocking. And there are other types of motions too that come into play, such as breathing and aromatic rings and so forth. But all of these motions have particular energies that are associated with them. And if you do the right experiment, such as a Raman experiment, you can detect what those energies are, and those tell you something about the character and the environment of the molecule that's present. So there are several general advantages to Raman, and I'm not going to go into detail for all of them, but I want to highlight 3 of them that are particularly important for the types of experiments that we would do with crystallization and polymorph analysis. As a trained chemist, one of the major things I appreciate about Raman is its specificity. So it's basically we again get particular energies for the bonds that are present in a molecule that are also specific to the environments in which they're found. So that specificity that can be related directly to those individual functional groups in the molecules that we're measuring become very good for interpretability. And that leads to excellent process confirmation, can detect process excursions, and are good for quantitative analysis as well. Also, the ability to be flexible in the measurements and either doing in situ measurements or non-contact measurements through sight glass make Raman very flexible in the way that experiments can be approached. And then the biggest thing relating back to the specificity, once again, is that last thing that's on the list, that's just process understanding, the ability to get molecular characterization information about the process that's taking place so that you understand what's happening better. Raman is again very good for this type of analysis because Raman is affected by the molecular environment. The Raman spectrum of a particular molecule is affected by the environment in which it's found. So in a pure material, that basically involves the interaction between the molecules, in the like molecules in the sample. But that can also extend to situations where you're in a solvent. So in this case, water molecules are pictured around the molecules of interest, and the water will have an effect on the spectrum as well. And when you're in a liquid, there's freedom of movement. So that degree of freedom means that the molecule will see various environments over time. And essentially, the spectroscopic measurement that you're doing you will see the average effect depending on how much time the molecules spend in proximity to each other, in proximity to the solvent, how the solvent surrounds that, and that's affected by concentration in turn. And it's all based on the thermodynamics of the situation. Once you transition into a solid, however, then things become a little bit different depending on the type of solid that you have. So if you have an amorphous solid, the order is not as strong, and so you will have basically different environments for the same functional group in molecules throughout the solid matrix that's present. So you'll have a diluting effect in a sense, in that you will see broader bands, that a little bit weaker bands with amorphous materials. But once that material becomes crystalline, then you have some interesting effects and some interesting things that can be used with Raman spectra for those crystalline materials. So in a crystalline solid, the order is very, you have very strongly ordered materials such that the particular functional group in a molecule sees the same environment from one molecule to another within that crystalline matrix. And if the order changes, such as what you have with different polymorphs, then the bands often become different because the environment changes for the functional group within that material. And so that's why different polymorphs can oftentimes give different Raman signatures. And that can extend to we can extend that discussion also to different different phenomena, such as what you see on the right there with carbamazepine. Once it becomes hydrated, water doesn't respond particularly well, or Raman doesn't respond particularly well to water, so you won't necessarily see the water in a dihydrate like you see with carbamazepine. But the molecular entities of the carbamazepine, their environments change because of the insertion of water into the crystalline matrix. And so the presence of the solvate or hydrate or whatever other solvent that might be present in the crystalline matrix then affects the Raman spectra, typically very significantly. And you can extend that same argument to salts as well. So the Raman spectra become different as the crystalline matrix changes because the environment of the functional group changes. So Thomas described a couple of experiments briefly that we did when we were using the Technobis device. And again, here's the setup that was used for the experiments with the Tornado instrument interface to the Technobis crystalline. And there were two target molecules that were examined with the studies that we did. One, as Thomas mentioned before, was the mefenamic acid, where we were following the conversion of form 2 to form 1 in ethanol. So you can see the experimental conditions here. And as Thomas mentioned, the transformation in this particular case was finished in about 10 minutes or less. And so, again, quicker measurements, high quality measurements, the faster the better in cases like this, to be able to follow the process, detect the endpoints, and understand the process in the best way possible. You can see the parameters that were used, and I'll just, these are fairly standard, except I will go to the bottom and just simply call you to your attention the fact that continuous collection was used in this case with 160 milliseconds with 30 averages. So we were collecting spectra every 5 seconds for this experiment. You can see the resulted spectra that were obtained for this set of experiments. You can see there's a bit of a baseline the effect here that is seen. And so if we do a baseline correction, we can get rid of that effect. And you can see that there are several places where the data or the spectra are changing. And those can, anytime you see changes, those can be useful in interpreting what's happening. Here's a little bit closer look at this, and I'll call your attention to two particular areas of the spectrum that turned out to be interesting. One was the same region that Thomas showed you earlier, which is the carbonyl band at 1676. And that band was represented form 2, and that band disappeared. So form 1 had no such band present in its spectrum. And so we can simply latch on to this band very easily in the carbonyl region, which is, the carbonyl region is often a diagnostic area for Raman spectra when we're looking at dynamic processes such as crystallization or reaction monitoring. And in this case, we could follow that very nicely, and we can see a trend. And so if you're just interested, depending on the level of interest that you have in terms of what you're using the PAT tool for, if it's just simple trend, monitoring the trend, we can again look at that peak disappear over time, and we can look at the trend in that peak disappearance to get some kinetics information. But I'll also call your attention to another region of the spectrum, which I highlighted previously, and this is a region where the carboxylate peak appears. And oftentimes, or hopefully, when you see a peak disappear, you'll see other peaks start to appear. And this one was an interesting one. You can see that that carboxylate peak was present in a smaller intensity, which increased over time as the crystallization or crystal transformation occurred. But if you look very carefully over in this region, closer to 1500, you can see, if you look look closely, there is a peak that starts to form here that was not present initially in form 2, but does form as the crystal transformation takes place. So if we look at that again, we can look at the kinetics a little bit differently. If we ratio to that band, the kinetics become a little more defined with that. But we can also do other types of analyses that gives you more information. So again, if a simple trend analysis is what you're after, that's possible. But if you want to understand more and delve into the data, you can oftentimes dig out quite a bit more information about your process as you look at the spectrum more carefully. One technique that we use for this is called hard modeling. This is with a software called PeaksAct, and we can derive some very interesting information. So if we look at that region between 1360 and 1540, you can see that there's some interesting deconvolution that we can do to get additional information about what's happening. So that peak that I pointed out, the carboxylate peak over just above 1500, you can see that forming as the process proceeds. You can also see some other underlying peaks that can oftentimes help you identify, for example, intermediates to understand that process better that you're examining. Another way to look at the data is by a technique called alternating least squares and multivariate curve resolution, and that's what we're doing here. You can see the two plots, the initial form 2 is in blue. The multivariate curve resolution allows us to pick the data apart and see the differences that may occur between form 2 and form 1. And so you can see the carbonyl band, which is very obvious over here, but there are some other more subtle bands that are present throughout the spectral data that give us an opportunity to look at this a little differently. And we can also follow the trends with that through that analysis as well. And if we look at that a little more carefully, we see, compared to the other analyses that we did, perhaps a little bit more distinct indication of the endpoint in the data based on the data that we see through the multivariate curve resolution. So by this, it looks like the endpoint was reached maybe a little bit sooner than the 10 minutes that was allowed, maybe even up to 7 to 8 minutes into the analysis is when we see a consistent level of form 1 over form 2. So there's some interesting observations that you can make with the Raman data through this process. There's probably possibly a few more distinct peaks in form 1. What does that say about the crystalline order? The kinetics are quite easy to ascertain. And one of the more interesting molecular level observations that we can make is that there's a disappearance of the carbonyl band, which suggests the deprotonated form perhaps dominates in form 1. Or we can look at this a different way. If we process the data a little bit differently, maybe we still do see a carbonyl band that's much broader and much less intense compared to the original carbonyl band that we see in the starting form 2. So again, the possibility or relating this to some of the other data like X-ray that you can start to piece together some molecular information about the crystalline form that you're seeing. So all this information leads to a better process understanding. And then the carbamazepine study, and again, I won't go into too much detail. Thomas already mentioned it's a much longer process than the mefenamic acid. So we were basically doing collections over 15 seconds to follow this particular process as it occurred. The pictures that were shared, this is shared in the application notes that we put out of the needle-like crystals going to the block crystals. Here's the spectral data, and you can see there's differing levels of intensity based on how much solid material is present. But if we do some corrections, do some normalization to the IPA band, and do some baseline correction, we can see some areas that are very interesting. One area Thomas already pointed out, which is down here in the lower level in the lattice bands, but there's 3 other areas that I'll highlight as well. We can see in that lattice band area, Thomas already showed this, but form 2 converting to form 3, a very distinct peak pattern change that occurs. And this can be watched over a period of time where we see the change take place over the course of a few hours. And once we see this change take place, this can be characterized, and the reaction or the crystallization can be followed dynamically over the period of time in which we're making the measurements. So this becomes a very useful tool with what we're doing to try to understand the process, both from the molecular point of view and also just from the standpoint of the kinetics and the thermodynamics as it's taking place. There's also some other peaks that are of interest here. There's a peak in the region around 874 wave numbers that's strictly related to form 3. So that becomes a very nice distinct peak to follow. There's another one in the 1490 area, probably in Amid, where we can also see it's directly related, distinctly related to form 3 as well. And then in the aromatic CH stretching region, we see something similar to what we saw in the lattice bands, where you're looking at spectral pattern changes that allow you to follow the process very distinctly as well. And again, if you're interested in a simple trend plot, we can use, for example, that peak at 874 wave numbers to look at the crystal transformation as it's taking place to get a better indication of the kinetics of the process. So the observations here that, again, the kinetics are quite easy to ascertain. This process is slower evolving compared to the methylamic acid, but again, the endpoint's rather easy to determine. And the chemical information that you get is intriguing with the involvement, for example, of the amide band and the aromatic CH band. So again, relating that molecular information back to something like the additional data that you would get with X-ray, for example, could be very interesting. So on the Raman side, what we try to do is provide measurements that you can trust. So tools like the Raman, the HyperFlex Pro Plus, and the Technovus Crystalline, in combination, provide excellent tools for crystallization process development. And the Raman is a value-added PAT tool for this process development and for process monitoring potentially in the future as well if it gets carried into production. So it allows for chemical insights for process understanding, allows for development of the understanding of the kinetics, and allows for endpoint detection for process efficiencies. And nothing's more expensive than process analyzer that fails to deliver. So using the best tool to help you understand your process is always paramount. And I want to just acknowledge the collaborators and colleagues who participated in this. And I'll go ahead and turn this back over to John for further information.
Thank you, Thomas. Thank you, Mark. We've had plenty of questions. A very interesting session there. We've had plenty of questions, so hopefully we'll get a chance to go through those. If I don't get to any questions people have asked, these questions will be passed along to Mark and Thomas so that they can follow up with you online. But we'll try and cover as many as we can now. So first question, is it easy and simple to get a good Raman spectra through attachments to the crystalline? I guess that's for Thomas.
Yes, it's very easy. We work with if a customer wants to have Raman put on the crystalline instrument, we work with you to build the brackets and adapters so it fits, and just all you need to then do is just plug in your Raman spectrometer and it's ready to go.
Okay, and how do you deconvolute solution spectra from the solid state spectra for the same material?
I guess that one would be for me. That's an interesting question, and one that becomes very it's a subject of some research that's going on actually. There's different ways to do that. You can oftentimes do that in a different experiment where you can aggregate the crystalline material and segregate that from the solution material. There's also some probe designs that can help you with that. So there's various ways to do that. It may take some additional experiments, beyond looking at the type of development we're talking about here. But there are ways to sort that out and get more specific information with respect to what's in solution, what's in solid form. The solid form also typically is more distinct, so that's helpful too. Most of what we're seeing here is going to be the solid form material. It's harder to get at the solution material when solids are present.
Okay, and how does the solids concentration affect the spectral quality?
Typically, the more solids you have, the better your spectrum is going to be. So you're going to basically see better as the solid content increases. You'll be able to follow that with the intensity of the Raman data.
Okay. Another question about the crystalline. In the case of measuring in situ in crystalline, is the Raman probe inserted into the vial, or does it measure through the glass vial?
So it measures through the glass vial. In this instance, we used quartz vials because we know glass has some Raman shift of itself. So the optics are built into the crystalline, and it uses the optics to just pass the beam through the vial and then back out.
Okay. Another question for Mark, I guess. Is there any extra information in the low frequency area of the spectra? And also, what do you think about the coherent approach? I guess you know more about that than me.
Yeah, I haven't dealt with the coherent approach, so I'll just simply say that I don't have a lot of experience with that. But on the low wave number side, that is an interesting question, because there are bands that are very sensitive in that area to crystal changes, solid state changes, and so that becomes an excellent area to look at. So there are adapters that would allow the spectrometers that you'll be using to go into that low wave number region. And that can provide some very good additional information. The information is hard to interpret, but it does give you a priori looks at the transformation that's taking place, and enables you to follow that quite nicely compared to even the main part of the spectrum. So it's a good area for use for looking at Raman with transformations.
Okay. And what is the signal to noise ratio of a Raman spectrum like, generally?
So that question can only be answered with specific circumstances. So the signal to noise ratio can only be calculated really with each individual analyte in each particular situation that you're making a measurement. We didn't do in these particular measurements any signal to noise calculations, so I would have to do that in order to give anybody numbers on that. But it's a case by case situation.
Okay. And for the Tornado Raman probe, what's the minimum working volume?
Well, the probe can be designed for different types of volumes. That's part of the flexibility that we build in. So a standard, if we have a standard probe, we'll just say it would be that the 12 millimeter diameter probe is sort of the standard off the shelf. But the probes can be made with different diameters to accommodate different volumes. And of course, you can always do a non-contact measurement, such as what we were doing here, to accommodate smaller volumes too. So we have a great deal of flexibility in how to adapt to particular experiments that require different types of probes.
Okay, we have a question here about someone that's worked with Technobis apparatus in the past, coupled with Kaiser Raman. And they've said that in the past there's been issues with thermal degradation induced by the Raman probe. Is the Tornado probe providing enough signal while providing reduced laser intensity?
Right. Well, that goes back to, I made a passing reference to our adaptation to ATEX, and what we do there is we are working at 35 milliwatts. So a standard experiment would be, if you're using full power, would be 495 milliwatts. But we've proven that with what we do with the HTVS design, we can get better signal throughput by comparison. So we can make measurements into lower laser powers that are difficult to make with instruments that have standard designs. And so with an experiment like what we're talking about here, that carries over to the fact that you have the capability to lower the laser power if there's issues with degradation. And so that would allow for better measurements to be done when the laser power has to be reduced to protect the sample.
Okay. I have a question that's probably kind of directed both of you. Do you have any case studies on co-crystals?
So we have several, we have application notes on our website about co-crystal screening. I also did a webinar earlier this year, I think it may have been for Scientific Direct or a conference on co-crystals, and that can be found on our website. But there's nothing at the moment from Technobis' side on detecting co-crystals with Raman, but I know it is possible.
Yeah, I will just add that I have personal experience with working with co-crystals in my past, and so yes, Raman is a good tool oftentimes for co-crystallization specifically.
So we have a question about, in terms of understanding polymorphism, is the Raman technique complementary to PXRD, and how does it help to determine the phase purity?
Yes, so it's completely orthogonal and therefore complementary. XRD and Raman are good sets of data to put together to better understand from a molecular level the crystal structure that you're seeing with the X-ray. And basically, I'm sorry, what was the second part of the question? Could you repeat that?
The second part was related. I've actually gone. The question's been resubmitted. Actually, can the person resubmit the question? Apologies for that.
Is it about the phase purity?
Oh, phase purity.
Okay. Phase purity.
Okay.
So yeah, you could create a calibration curve with the Raman. So you take pure one form, put pure the other, and then mixtures of the two, and then you track a specific peak's response based on how much of the contaminant or unwanted form is present. So you could create a calibration curve, which then you pick out and say, real time, this is the response I'm getting, therefore it corresponds to this concentration.
And I will add to that, there's a technique for quantitative analysis called hard modeling, and it allows you to do that with fewer calibration samples. And so that becomes, for a situation like this, I think it's ideal because it allows you to do quantitative analysis without the long drawn out process of having to do model development in a more standard sense. So yeah, Raman can be a good tool for that purpose.
Okay. So if you have a single polymorph, are the Raman spectra influenced by the size and crystal habit?
They can be if the environment, if it changes the environment of the crystalline form, then anything that does that will change the Raman, or could change the Raman spectrum because of that change in environment will have that effect.
Okay. And a question for Thomas. In the carbamazepine example, how did you validate the polymorphic forms in that case study? Did you take a sample for X-ray structure analysis, and does the particle size have an effect on the Raman spectrum?
So in this instance, we didn't sort of validate the form that was being produced. What we essentially were doing is recreating two papers. So someone had done an experiment of that conversion, and I think I had the images in my slide. And they had also done offline Raman measurements in a second paper. And what we wanted to do was just combine them both sort of into that one experiment with the imaging. And I think the imaging was sort of, again, our way of confirming what was happening with the Raman spectra. So we started to see the change in the Raman. We're able to put that into the imaging position, and then observe the needles starting to disappear and the blocks starting to reappear.
Okay, there's an interesting question. Have you ever experienced a case in which Raman spectroscopy has been used to study disappearing polymorphs? And if so, is there any kind of information about the possible factors affecting such phenomena?
I mean, the principles would be the same. You're looking for a change in the Raman spectra. So if peaks start disappearing, then that can tell you obviously that the solid form is changing and the polymorph is disappearing. And with the analysis, I think Mark showed about the the information about the bonds being involved. If a peak disappears when it's involved in a certain bonding pattern, but then that disappears, that could tell you, that molecule, that part of the molecule is no longer being involved.
Okay. We're almost coming up to time, but a few more questions, I think, to finish. How can one differentiate amorphous and crystalline material using Raman? Is it possible to get the percent amorphous in the crystalline material or vice versa?
Yeah, it is possible. Again, using the calibration approaches we talked about previously, but usually the crystal form will have much sharper, more defined bands and more bands that are present in the spectrum, whereas the amorphous material, because of the diluting out of the different environments that each functional group will have in an amorphous material, those bands will be typically less sharp, broader, and fewer. And so you'll typically have very distinct differences between crystalline materials and amorphous materials with regard to the Raman spectra.
Okay. We have a question: is it possible to connect the Raman probe? Can it be adapted in some way to a microscope setup?
Yes, and there's we have done that in our facility, looking at different visualization tools. So yes, there is the possibility to do that. And of course, you have with the Techno. I should let Thomas comment more on this, but with Technobis, obviously you got the visualization tools that come along with the ability to do the Raman as well.
Okay. So we've still got some questions. I'll just check a random question, I think, and then we'll draw a close to proceedings. And as I say, anybody that I've not got round to asking their question, I can pass on the questions to Mark and Thomas. Final question is, what if you don't know the structures? I take it that you need to know the full 3D structure before being able to assign the peaks and to understand there's sometimes subtle differences.
No, the spectra are interpretable a priori. I mean, it always helps if you know something about the structure initially, but you can relate the structural features back to their molecular, what those bonds are telling you. And so you can get a priori knowledge about the bonds that are present, the functional groups that are present, and that can help to construct the molecular structure that you're dealing with. But the vast majority of people, when they do these experiments, know the structure they're dealing with, or at least have an idea of the structure they're dealing with at the beginning of the experiment.
Okay, great. So once again, thanks Thomas and Mark for a really interesting session there, and thanks to Technobis and Tornado Spectral Systems for kindly sponsoring and organising this this event. So as I say, the slides will be made available, the PDF will be made available, and the webinar will be archived so that you can view it again or share it with colleagues if they'd like to view it. So thank you very much, and I wish you all a good afternoon, good morning, good evening, depending on where you are, and keep checking our website for future webinars. So thank you all very much, and we'll see you again soon. Thank you.